When I say feedback, it means that you're going to use sensor data to control the manipulator. So what we've seen so far is we've derived the equations of motion. So equations of motion using the Lagrangian. So equations of motion were derived as follows. We took the Lagrangian, and then we did dl dq dot minus dl dq equals torque, where tau I wrote, well, let me write it as q. Let's call this I think j. Okay, and then what happened was, in that case, when we did this for, say, the double pendulum, it ended up being a system which looks something like this. So we lumped everything which was related to theta double dot in the A matrix, and then the B was whatever was left. Right? It turns out that these equations actually can be written another way, which is better for interpretation. These equations are written as m q double dot plus c q dot times q dot plus gq equals tau. Okay, so what are these various terms? This M is known as the mass matrix. P is known as the, or CQ. Let me just write it as MQ. CQ Q dot is a term which is associated with Coriolis acceleration / torque, and G of Q is the gravity torque, and tau is the external torque. Okay, so that's how almost any equation of a manipulator will look like. It'll always have those terms, M, C, Q, G, and then the external torque. Now, for this particular simplification which we had here, you can also write it as this, in this fashion, as follows: MQ Q double dot equals tau minus CQ Q dot minus GQ. Okay, what I did was I just moved the C and the G on the other side, and what we have here is, this is can be written as A theta double dot, and this thing is B. So this thing, the way we wrote it down earlier, A theta double dot equals B, is the same thing. It's just a simpler way of writing this complicated expression. The reason I write it in this fashion is because once you have that, you identify those terms, you can do things with the control of the system, and that's why I wrote it as this expression, which you'll see in a textbook. If you look at the equation of manipulator, it will be something like this. But it can also be written as this equation. And in fact, that's what we need to do in order to solve for Q double dot. We need to write it as A theta double dot equals B. Okay, now that we know how the equations look like, let's think of how to control the system. When I talk about control, I need an objective. What is the objective of control? There are two objectives here. One is, and we look at both of them. So two objectives. For control. Number one is set point control. An example would be, you want the pendulum to be inverted balance an inverted pendulum or keep a pendulum in the vertically upright position when gravity is pointing downwards. If you don't have a controller which is keeping the pendulum upright, then the pendulum will fall down, right? And so you need to have some control. So example would be, I'll just draw a figure. Kept upright. The second one, which we are also interested in, is what is known as a trajectory control or trajectory tracking control. Here, what we're interested in is not just keeping it at one particular set point, but we want it to follow a trajectory. So, for example, if you want a manipulator to, let's say you modeled a human leg or a robot leg, and you want the robot to kick a ball. So then in that case, you need the leg perhaps to follow a trajectory. So that would be something like this. Or maybe you just want it to go straight out. So it just need to go like that. Another example is, so kicking a ball. Another one is an example we've done before, which is you have a manipulator and you want it to track a circle or some curve. Track a circle. Okay, so the best way to motivate this is to look at a simplest possible system which has the equations which look similar to a, a manipulator. And so we said that the equations of a manipulator are m q q double dot plus c q q dot plus gq equals tau. Okay, a simplest case is, let's assume this to be a constant m q dot. So this c q q dot q c as a function of q q dot is just a constant c plus gq. I'm just going to make it proportional to q, and then let's just put f. So this happens. So this is a simplest way of, just a simple example. Simple example. Okay, so these equations are what? Equations of a spring mass system. Right? So if you have a spring, a damper, and a mass. So this is K, this is C. That's F, and then Q is the degree of freedom associated with the movement. So it's a spring mass system is what we have written down here. This is equation of a spring mass damper system. Okay, so we'll sort of build an intuition based on this system. You've probably seen this before, and then we'll go to N-link manipulator based on this. Yeah, so what I'm going to do is I'm just going to move things around. So let's take this equation and divide the whole thing by m, divided by m. So I have q double dot plus c divided by m q dot plus k divided by m q equals f divided by m. For this example, let's look at the case where there is no force. So what we're looking here is free vibrations. So for example, in your ME320 class, I think you have vibrations, right? So this is the equation you probably looked at. Now, if you remember from that class, if you want to simplify these equations, what you do is you write a natural frequency, which is square root of k divided by m, and then you define a damping constant equals c divided by m. So the damping constant is, so I need to put omega n equals square root k divided by m, and if I do that, I end up getting c divided by 2 square root m times k. So these are the two important quantities which you need in describing the motion of a spring mass system. There's a damping constant, I think it's called eta. Check. No, it's eta. That's not eta. You know what that is? What symbol that is? I think it's psi. Okay, psi is the damping constant. Okay, now if you remember from that class, there are three cases which you need to look at. One is when psi is greater than 1. This happens when, so psi is greater than 1. You can see from this equation that in this case, c would be greater than 2 square root m times k. This system is called overdamped. Psi is equal to 1. Here c is exactly equal to 2 square root mk. This is critically damped. Then we have psi is less than 1. This is c is less than 2 square root m times k. This is the third case, it's underdamped. Okay, so why do we care about overdamped, underdamped? Well, they define how the system would behave when you pull the mass and let it go. Okay, so what will happen is if you look at a plot of q, that is the deflection as a function of time, you will see the following. If you have an overdamped system, so let's say that in all cases, I'm going to start the system with some So this is 0. So you pull the system. You actually, in this case, since Q0 is negative Q, you're actually compressing it and then letting it go. So when you let it go, depending on the damping constant psi, you'll have 3 responses. The first one, let's say that's the overdamped one. It'll be something like this: over damped psi greater than 1. Okay, on the other side, if you have underdamped, you will see that it'll actually start oscillating. Okay. This is underdamped. And then the final one is critically damped. That would be something like this. Critically damped psi equal to 1. So what I did was I circled the points where this damping goes close to 0. So here you can see that this is the point approximately where the unwanted displacement goes to 0 for the critically damped case. It's about the red dot for the underdamped case, and then the green dot for the overdamped case. So what you see is that if the system is critically damped, it will go to 0. Q tends to 0, or Q goes to 0 in the shortest time. Okay, and that is important for us because when we are looking at a system which behaves, say, like a spring mass system, normally what happens is, let's say a bridge is modeled as a spring mass system. Because of disturbance, let's say wind or whatever that is, Q, it starts off with an amplitude, and then you want it to go back to 0 displacement, and the faster it goes to 0, it's considered to be more stable, because if it takes more time, then you'll feel those oscillations, and that's not good. So we always care about getting the system back to 0 in the shortest amount of time, and that's why a critically damped system is very important. Okay, in fact, one of the things you do is when you want to design the system, you want to ensure that the damping is such that it is critically damped. Okay, and you can do this in a number of ways. One is you can remember it needs to satisfy this equation. So m is usually not in your, well, m is the mass of the system, k is the spring constant, c is the damping. So usually m and k are whatever comes to the system, but the damping is something which you can tune by putting dampers, for example. Okay, so this basically motivates the following thing, that is, you want to ensure that the system is critically damped so that it goes to 0 in the fastest amount of time. But the problem is this: if you have a mechanical system, which is, I wrote it down earlier, mq double dot plus cq dot plus kq equals f, you may not be this m and c and k may be different at different frequencies. M may not change, but c and k will change at different frequencies. So then the good thing about control is that you can actually design f such that this system is always critically damped, no matter what c and k and m is. Okay, so what we'll do is we will design a feedback controller f as a function of q dot, such that the system is critically damped. Okay, so what is that function? Well, the simplest way is to take what they call the proportional derivative controller. So kpq minus kdq dot. This is known as a proportional derivative controller. The proportional part is kp times q. The derivative part is minus kd times q dot. You can think of the proportional part as the spring part, and the derivative part is like a damping part. Okay, and then kp and kp and kq or kd are user chosen gains. These are numbers you choose, and you can put whatever you want. Now, let's see what we can do with a system like the spring mass system with a proportional derivative controller. Plus kq is minus kpq minus kdq dot. Okay, this is f. Okay, f is something you can choose in whatever way you want. So let's do this. Let's move things around. Plus c plus kd q dot plus k plus kp q equals 0. Okay, note that these numbers are user chosen. Okay, that can be tuned, but one thing insight we got from the simplest free vibration example is that if the system is critically damped, it will go back to 0 in the shortest amount of time. So that condition is the critically damped condition, and that is, it was c plus kd equals 2 square root m k plus kp. So where did I get this from? If you go back to this equation, this came from the c. Where's that? Here. This c was whatever is in front of q dot, and this m was whatever is in front of q double dot, and then k was here. So I just do the same thing here. I just picked up m, c plus kd, and k plus kp. This is similar to c equals 2 square root mk. Okay, so what we can do is we have this condition. This is the only condition which needs to be satisfied for the system to be critically damped. We care about critically damped system. We have two ways to achieve it. You could keep kp whatever you want and tune kd, or tune both of them, or keep kd constant, change kp. So what we'll do is we'll just solve for kd. Okay, we'll keep kp is fixed. That is, you will choose a kp, whatever you want, 10, 15, whatever you want, and solve for kd. So instead of tuning two numbers, we just tune one number, just make our life easy. So we square the two sides, squaring both sides. C plus kd square equals 4 times mk plus kp. So I'm going to expand that out. C square plus 2c kd plus kd square equals 4m k plus 4m kp. So writing it in terms of a quadratic equation in kd square, we have kd square plus 2ct plus c square minus 4mk minus 4m.kp. So you notice that this is a quadratic equation kd, and the solution to this is given by the well-known formula for solving quadratic equations. Kd equals minus 2 plus or minus b square. So b is this 2c square minus 4 ac. A is 1. C is c square minus 4mk. The whole thing divided by 2 times constant here, so 1. Anyway, so what you'll see is that you'll get 2 values. One value is definitely negative if you use the negative sign. The gains cannot be negative. A negative gain implies that it's not feedback anymore, and the system will go unstable. So we'll take the positive root, and then we get kd equals minus c. I'm forgetting something here. This should be 2c minus b. Okay, c plus 2 square root k plus kp times m. Yeah, so this was the equation we were after. Okay, what we'll do is kp and kd are designer's choice. We could choose either of them. My suggestion is just choose kp and obtain kd from that equation. What this does is it basically ensures that no matter what the spring constant is, no matter what the damping is, you'll always get the system to be critically damped. So it'll always go to 0 in the minimum possible time. Okay, and so I'll show you some code which does this. That is, it sets these. So I'll show you the system without any control, and then we'll do it with critically damped control and see how the response is faster than that without any control. Okay, so I wrote some code which essentially solves the equation of an uncontrolled system. So you can see it's x double dot is minus k divided by m c divided by m. Here x is q from my notes. So here the system is initialized with some initial condition 0.5. So it's pulled by 0.5 and let go. And I chose some mass, damping, and so on parameters. So if you run this, you see that it starts at 0.5 and then it oscillates, goes close to minus 0.1, and then and I can do this for more time, and then maybe you'll see the difference. Let me just increase this to, let's say, 20 seconds. So now you can see it overshoots and then overshoots a little bit more, and then it's almost 0. So it takes about 7.5 seconds for the system to get back to 0. Now what I can do is I can turn on the controller. So I chose a KP10. KD came from that formula I wrote down in my notes. So this is my uncontrolled system. Now I add some control. Here I have same equation as before, but now I have k plus kp, k plus c plus kd, and then run this. And then you see that it starts at 0.5, but within 2.5 seconds, it gets to 0. So using feedback control with the right constants, you can get the system to be damped.